Solutions in complex numbers. When we were solving quadratic equations, we had some situations where we had no real solutions as our final answer. Look at these three graphs of quadratics. Tell me how many solutions each of these graphs has. So that first graph clearly has two solutions, right? Because I can see these two x-intercepts right here. The second graph has one solution. Now we'll learn that that means there's one solution there with a multiplicity of two. Okay, and then if I look at this last graph here, it never crosses my x-axis. So, I mean, no solutions? We say that that's no real solutions. So that means it has two imaginary solutions. Imaginary! So we're now stepping out of the real number land and stepping into imaginary numbers. So this is where this idea of a complex number comes into play. Now, a complex number is a real number plus an imaginary number, and it's written in this form, a plus bi. So the real part comes first, and then the imaginary part comes second. So now where do these imaginary numbers come from? Well, negatives underneath our square roots. So I, this little imaginary number I, is equal to the square root of -1. So what would I square then be? Well, if I is the square root of -1, and I want to square it, well, a square and a square root undo each other. So it's -1. Oh, that just got real. So I is an imaginary number, but I squared is just -1, so it's a real number. So then what about I cubed and I to the fourth? Take a moment, consider those two. Well, let's think about it together then. I cubed could be rewritten as I squared times I, right? I squared, we know, is just -1, and I is the square root of -1, so I'm just going to leave it as I. So I cubed is really -1 times I, so -I. I to the fourth. Well, I to the fourth is I squared times I squared, so that would just be -1 times -1, which is +1. So I to the fourth is also a real number, 1.
Do you know we can graph complex numbers? The horizontal axis represents the real number line, and the vertical axis represents the imaginary. So to plot the point 3 plus 2i on the complex plane, simply move 3 units to the right on the real number axis, and then up 2 units on the imaginary axis. There's point A. What would we do for point B? -5i. Imaginary. Well, it's going to be on the imaginary axis. Down 5. All right, plot point C. C ends up in like my third quadrant. Okay, let's go ahead and simplify some of our square roots. Square root of -49. Previously we'd just say not possible, but now with complex numbers we can simplify this. So think of factors that we can break it down into. Well, first of all, square root of 49 is all good, but then it's times square root of -1, and square root of -1 is I. So my answer would simply be 7i. Look at B. Same idea. We know we have a square root of -1 in there, but now 18, ooh, perfect squares. So 3 times 6 doesn't help, but how about 9 times 2? Yes. Think through what comes outside the radical now. Square root of 9 is 3. Square root of -1 is I. Square root of 2 is square root of 2. So the proper way to write this is 3i square root 2. Really important to pull that I next to the 3 so it does not look like it's under the radical. Last, take a look at square root of -5. Square root of -5? 5 isn't a perfect square. We're just going to have to leave it. But what about that -1? We can pull it out. Once again, when we write this, put the I in front of the square root so that it doesn't look like it's possibly underneath the square root sign. Next, you try D through F. Come back and check your answers. As you check your answers, just make sure that you have the placement of I proper so that we don't have any confusion about the answer. This is the proper notation.
Oh, so now we can finish solving the quadratics that we left as no real solution. 3x squared minus 4x plus 3 equals 0. Well, it already equals 0, so I could try to factor and use zero product property. Multiplies to 3. But I need 3x squared. There, the crisscross method's not going to work here. I could try to complete the square, but my a term isn't 1, so I'd have to divide out that 3. So let's just use the quadratic formula. Okay, so I plugged into my quadratic formula, and right here at this step, I have 4 divided by 6 plus or minus the square root of 16 minus 36 divided by 6. Well, right here, I already can tell that I'm gonna end up with complex solutions, imaginary numbers, because I have that 16 minus 36 that's gonna end up being negative underneath my square root. That's called the discriminant, b squared minus 4ac. After doing my side note and simplifying my square root, I end up getting 2 divided by 3 plus or minus 2i root 5 divided by 6. Now there's still some more simplifying I can do, but let me stress here, it was important that we separated that denominator and have the real part plus the imaginary part. That's how we write complex numbers. The last thing I need to simplify is the 2 divided by 6 into 1 divided by 3. So final complex answer, 2 divided by 3 plus or minus I root 5 over 3. So we have 2 complex solutions. Let's try this again.
As we look at problem 2, we're going to solve this one using square roots. Let's isolate x squared. And of course, now we square root. Remember, you get 2 possibilities anytime you square root an x squared, positive, negative. Square root of negative 25 is square root of 25 times negative 1, so 5i. So we end up with 2 imaginary solutions, positive 5i, negative 5i. Take a look at number 3. I think you got this one. X equals positive 2i root 7 and negative 2i root 7. Did you write it in the correct order? Number 4, x minus 2 times x minus 2, and then I'll add the 9 and move it over. Whoa! Why? Why would we do that? We have x minus 2 quantity squared. There's nothing else around it. I can just square root right now. Remember to have your final answer in correct form. Complex number, a plus bi. So I can have x equals 2 plus or minus 3i, and you'll notice that I went ahead and separated it so that we clearly see 2 imaginary solutions. The form is important. Let's learn to have correct mathematical communication. These are conjugates of one another. A conjugate is when we simply change the middle sign. You'll see why this is important later.